Viceroy Sizer seminar. This is our second seminar since the fall semester has begun, and we will have two more. And today we have the great pleasure of having Dr. Asma Akbarram speak to us on the topic of blockchain and how it relates in particular with digital forensics and evidence. Dr. Asma is an assistant professor at the Tri-Cities. She joined this year in fall 2025, and she holds a PhD that she got from in computer and cyber sciences from Augusta University. And she's got a variety of interests, including blockchain, network security, intrusion detection systems, and the use of AI with network security at that intersection. She is also a faculty advisor for a newly formed Women's in Cybersecurity Group chapter at the Tri-Cities campus, and she'll be teaching a number of cybersecurity courses in the spring semester now. And I'm looking forward to this, and I want to remind you a couple of things before we get started. If you have questions as this presentation goes on, you can put them in the chat. We'll monitor them, and Asma will be leaving about 10 minutes or so towards the end for answering questions. Or if you want to hold on until the presentation is finished and ask them at that time, that will be also perfectly fine. Make sure to participate in the survey that happens at the end. So we're mindful of the time, and so I don't want to take it too much into this time now. Asma, when you're ready, go ahead and get started. Thank you very much for taking the time to present to us today.
Here, Asafo. Hi, everyone. My name is Asma Judariya Akbarfom, and today I'm going to talk about how can blockchain enhance trust in digital forensics and evidence. So as Asafo said, I got my PhD just recently, and my research focuses on blockchains and intrusion detection, and I'm the faculty advisor for women in cybersecurity. So enough about me. Let's talk a little bit about Walmart. In 2006 and later in 2017 in the United States, there was a disease outbreak, particularly related to leafy greens and in some sort of lettuce. So the retailers were trying to trace the contaminated source. They discovered that it was harder than they thought. It took them 7 days. It took Walmart 7 days to trace the origin of a single package of sliced mangoes. So Walmart thought it's insufficient and it had to come up with a better way to kind of be able to trace its supply chain, and also when there are a lot of returns in its products in order to improve them for the future. So it thought I should be able to trace my products from farm to fork, and it was a good idea. So what they did is they partnered up with IBM in 2017, and they used blockchain to trace their supply chain. And with that, instead of 7 days to trace a simple disease outbreak in contaminated groceries, they took only 2.2 seconds to track their system. Now, what is blockchains? Blockchains is a chain of blocks which are interconnected by cryptographic hashes, and every block contains data in reference to the previous block, which makes the entire chain tamper evident. And before a new block is added, the nodes in the network must agree on its validity through a consensus mechanism. And these consensus mechanisms are proof of work, proof of stake, and proof of authority. So why blockchain? The reason is that it's decentralized. Instead of one central authority controlling the records, blockchain distributes them across many nodes. And this means there are no single point of failure and no one entity can secretly rewrite the history. It's transparent. Everyone in the network sees the same shared version of the truth. That makes it easy to verify where something came from and how it changed over time, especially useful when multiple organizations are involved. It's immutable. Once something is written on the blockchain, it's extremely difficult to alter without being detected. That gives you a permanent tamper evidence trail, exactly what these kind of situations on supply chain or when few people are collaborating is needed. So we covered what blockchain is, but there are different types of blockchain. The one most people think about in the first place are the public blockchains like Bitcoin and Ethereum, and anyone can join in these networks. They can read, they can write, and it's great for transparency, but not always ideal for enterprise or regulated environments. On the other hand, we have private blockchains like Hyperledger, where access is controlled and only authorized organizations can participate. These are often used in supply chain, healthcare, government, where data can't be fully public. We also have the permissioned or hybrid blockchains, which multiple organizations share control and no single party owns the system, but not everyone can join. So choosing the right type depends on the balance between openness, control, and trust, and the choice is critical depending on the application. I know when people talk about blockchain, what we think of are the cryptocurrencies. And some people think it's simply in our imagination and blockchain is not being used that much. But it's not true. In reality, blockchain has moved far beyond, and now it is being used in a lot of major industries. So, for example, in banking and finance, Visa uses blockchain for cross-border payments and fraud prevention. In supply chain, we went over Walmart, which is good to track goods and origins. In healthcare and insurance, companies like Pfizer or even the FDA use it for secure medical records and claim verification. In government and energy, national agencies and power grids use blockchain for identity licensing or smart grid coordination. It's used in IT and travel, from logistic tracking to airline maintenance and digital passport. So blockchain is embedded in a lot of systems, and it is good in the real world for trust verification and transparency across multiple parties. Also, and beyond the industry, there are a lot of research going on the different frameworks and how we can improve them in all of these fields you can see here in machine learning, in cloud computing, scientific workflow, and in digital forensics, which we're going to talk about it today. But what is interesting and important in all of these domains is that we want the metadata of the data, and uh, we want to know where the information is coming from, who had access to it, who modified it, and so on. So that is called provenance. So provenance simply means the ability to track where something came from, what happened to it, and who interacted with it. And you can see in different domains, for example, in supply chain, it can be unique product ID or batch number, travel trace, or in digital forensics, it can be case number, investigation stage, and in scientific collaboration, it can be task ID and workflow. So domain needs provenance, what does a good provenance framework actually have to do? From looking at all those systems, the needs were surprisingly constant. First, you need access control. Not everyone should see or touch everything. Then, we also need a way to capture the information. We need a way to query the information, and another way to verify if this information is correct. We also need to consider each domain and its quirks, legal rules in forensics, timing constraints in supply chains, and of course, we need to look at the security. We need to know if these frameworks are scalable and testable. And we need to think of all of these needs before trying to create our own framework, which is based on blockchains. Now, looking at digital forensics, before I explain to you the phases, I want you to think of an example of digital forensics. In our case, it is when someone is being questioned by the police department and their laptop and phones are confiscated and they are getting the information out of their phones and laptops into the system. Now, when this is happening, there's going to be different phases that the data is going to be handled. There's going to be the identification, locating the digital evidence. There's going to be preservation, making exact copies, and analysis, examining the data using forensic tools, documenting it, and presenting it in the court. And these phases are handled by different people, which this is called the chain of custody. So in digital forensics, it's important to verify the chain of custody and to know who handled what evidence and who came up with what result while handling a phase of digital forensics. So for that, we look at different frameworks which are related to digital forensics, but there wasn't a comprehensive framework that did meet our needs. Therefore, we designed FrenzyBlock. So FrenzyBlock is representing the investigation stages. It keeps track of the version of the digital evidence, and it enforces access control and policy updates. And we answer different research questions that come up with such frameworks. How can we verify and manage multiple versions of the digital evidence? How can we log the provenance? How can we use and extract it? And what kind of access control method do we need? And this is the architecture that we designed for FrenzyBlock. So we have the users, which send their request to the framework. And on our blockchains, there are three main smart contracts: tokenization, access control, and provenance. And once the user sends the request, the tokenization smart contract makes a per case smart contract for every case. And when users want access to the information, there's going to be an access control smart contract who is going to make the decisions. And there's going to be a provenance smart contract that verifies the provenance of a case or cases. So smart contracts are self-executing codes on the blockchain, which they cannot be tampered with, and they're gonna be an output which is gonna be the same for everyone. We also have off-chain storage. Well, in the off-chain storage, we're going to have the files, and also sometimes we're going to send the provenance to the off-chain storage. We're going to see about it in the next slides. So the first algorithm is shown in this slide. And in digital forensics, it matters that to know that files aren't static. They get combined, filtered, decrypted, or merged. So for example, if we have case N, we have files A, B, and C, which are extracted from the person's phone. The person doing the analysis would analyze a file B and C and create file BC, and then again analyze file BC and create file BC2. And this can happen a few times. So what we want to do is we don't want to only log this. We want to be able to verify file BC2 was made of file B and C. Therefore, when we are making the tokens to save in the system, we create it from the original file's tokens. And therefore, if someone claims a file was made from B and C, we can kind of verify that. So this is one of the advantages. After that, we also have a role-based access control with stage authorization, which is kind of based on digital forensics itself. As you saw, there are different phases in the digital forensics. And if we just wanted to have a role-based access control, every person would have to go and change the accesses every time a case phase was moved and it was in another stage, but we wanted to make it dynamic. So in the blockchain access control smart contract, we will implement this role-based access control with stage authorization, meaning in every stage, the roles of people are the same, but what happens is their amount of access change. So for example, a person may have write control on the analysis phase, but during the presentation phase, they can only read. So this is done dynamically. So till now, based on some transactions, which is opening the case inside the blockchain, every time sending the access request and either denying it or accepting it, and provenance request, we have these records. We will have the case number when it was created, the initial block number that it was added to the blockchain. We're going to have the stage of the investigation, the client info, and the token dependency, and etc. But now that we have all of this information, how do we get them from the blockchain? For this, we thought of this algorithm, which is every time a transaction is made to a case, we hash them together and hash them with the future transactions as well to make a Merkle root, a single Merkle root for that case. And this is very important because by having this algorithm and saving that Merkle root in the blockchain, in the future, when the provenance information is extracted from the storage, and maybe our storage is malicious and it has modified the provenance information, then we can verify it with this hash to see if it was tampered with or no. And we're going to evaluate if this algorithm is actually working and if it's in good speed. So you can see here the entire tree for a single case and the Merkle root that the transaction is made of. So and here we are verifying the Merkle root with the information we extract from the storage. So in order to test our framework, we created 10,000 blocks and 100 synthetic cases. And we send random transactions, creating cases, access control, provenance into the blockchain. And we change the stages of the case periodically to see what happens. So to evaluate how well the frenzy block handled the provenance retrieval, we compared the three methods. We have the brute force scanning the entire blockchain to find the case history. We have smart brute force scanning, but only from the block where the case was started. And we have our proposed method, which is retrieving directly from the off-chain storage the provenance information and verifying it using the Merkle-based algorithm. So you can see see the difference clearly when the number of blocks increase. With the brute force, it becomes very slow when the number of blocks are more. But and the smart brute force is slightly better, but our method is much better in terms of time retrieval time. So a scenario would be that the judge wanted to verify the chain of custody of a case. What it would do is get the information very fast from the off-chain storage and then give a request to the blockchain to verify the Merkle root with that information. And then if it was the same Merkle root, that means the storage was not tampered with. If it was changed, then we could use smart brute force, meaning look at the first block that this evidence started from, and then do the smart brute force to retrieve the data. And also the transaction processing times are slightly higher in our method, but it's because they are more complex than simple read and write, and they're negligible. So beyond performance, the big question is Frenzy Block actually secure? At the core, the framework is designed to provide three guarantees: integrity, accountability, and non-repudiation. So, how do we prove that these properties still hold when adversary actively tries to break the system? So, what happens when also Frenzy Block is combined with other protocols or deployed in a larger environment? Does it still stay secure? So, is it secure in a modular manner? So these questions directly lead us to a formal security analysis to look at, and what we choose is the UC one because it can kind of tell us if a system is secure when it's combined with other protocols, run concurrently with other operations, or attacked with an adaptive adversary. So UC supports modular design. You can treat this protocol like a Lego block, prove it once, and you can reuse it anywhere. So if a framework is secure under UC, it can be combined with other frameworks, and it could be part of a bigger picture. So what does UC actually give us? It's a guarantee that a protocol remains secure. The way UC proves security is by comparing two worlds: an ideal world where everything works perfectly with a trusted party, and the real world where everything is executed as an actual protocol. So if an adversary can tell the difference between these two worlds, then the protocol is considered secure. So, but instead of jumping from the ideal to the real in one step, UC allows us to move gradually through hybrid models, hybrid 1 and hybrid 2, and etc., which is replacing each one is replacing the ideal world components. We're going to see in the future slide what I mean. So this is what it is for the UC security analysis of Frenzy Block. Here we start with the ideal world, which is our perfectly secured reference with no leakage and no tampering, as if the adversary never got any extra information. Then we move one step by step with the hybrid 1 and hybrid 2. So each time making the model more realistic. In hybrid 1, the adversary is allowed to observe but not interfere. In hybrid 2, we introduce contract style logics now that the system behaves more like a real blockchain protocol. And in the last hybrid, which is the real world, we add a signature scheme, and the adversary is fully allowed to attempt modifications, but these modifications can be detected and rejected. Notice like we have different simulator boxes between each steps. These are essential in UC proofs. The simulator acts as a fake interface that imitates the real protocol from the adversary's perspective. And its job is to fool the adversary into thinking nothing has changed, even as we replace ideal behavior with the real mechanisms. So at every step, we prove that the adversary still can't distinguish these hybrids from the previous one and that the difference is negligible. So the real protocol is indistinguishable from the ideal one. So I will just simply explain these. I'm not going to go into much detail with these proofs, but this is kind of a figure that would show our first step. So we will have the ideal world, we will have a hybrid one. Our hybrid one is as our real world. And then, as you can see, a different flow of information here, the environment, which is interacting with the ideal world. The ideal world would send this to the simulator, and then the simulator would leak it to the adversary, and then the adversary to the environment and back. So what happens here is we want the environment, also the adversary, not to know who it's interacting with. Is it ideal world and the simulator, or is it hybrid one? So, so after that, we are gonna put the hybrid one as our new ideal world after we prove that the last step emulates each other. Here we will have the hybrid 2 as our new real world. And at the end, our hybrid 3 and hybrid 2 and its simulator. You can see the snapshots of the code. So for example, in hybrid 2, we didn't the adversary could not go and modify information, but in hybrid 3 it can. So the simulator is there to kind of make the situation similar, so the adversary doesn't know who it's interacting with. So what we can see here after that is this mechanisms that were for signature detection, which was added by the simulator. So these proofs are kind of complicated, and here I've put some of the snapshots so you can see, like, for example, this is for only hybrid 2, and also it will have its own simulator. So every world and the simulator would have their own kind of proofs, and we have to run it step by step to see if they can emulate each other. So at the end, we have, well, here I didn't go much into detail, but we will have formally shown that even on a powerful adversary trying to do its best to distinguish between the ideal execution and the real execution of frenzy block, it can't tell the difference unless with negligible probability. So in other words, from the adversary's perspective, the real system behaves just like the perfectly secure ideal world, which is exactly what UC aims for. So it remains secure even when combined with UC secure protocols. So if we have other UC secure protocols and Frenzy Block is part of those, the whole system will be secure and it wouldn't have any extra leakages. So this was for only one agency. What if there are more agencies trying to collaborate together? There are, and this can be, for example, if a police department wanted to collaborate with the FBI and they had their own blockchains. And usually these blockchains have different protocols that they cannot understand each other. Therefore, in order to manage this kind of situation, cross-chain is used. So not particularly yet in digital forensics, except our method, but in other methods such as Vesago, which is for supply chain, or synergy chain or ARC, which are more general, they are used to connect different blockchains. So there are different methods, such as a notary scheme, where a trusted or semi-trusted party validates events on one chain and reports them to another. We have it on relay chains, where one blockchain runs a light client of another chain and verifies it state directly. We also see that they have some limitations. So, for example, they're not for digital forensics. They don't really look at the provenance capture or query. They just try to connect these blockchains to get to each other. They don't have, some of them don't have access control, and they don't do any security analysis, and they don't consider the architectural scalability. So we designed Frenzy Cross, which the goal here is not to replace individual forensic blockchains, but let them collaborate without breaking the trust guarantees. And a few research questions arise. How can they do this securely? How can the provenance be verified? Sometimes when they need to verify the, for example, provenance, but they don't want to share the information either. And what happens if more than two agencies are trying to collaborate and a few want to have this? So this is the architecture of Frenzy Cross. We have blockchain A and B. From each of them, they have trusted nodes. Their trusted nodes join bridge chain. And bridge chain is an intermediary between these blockchains, which is a trusted party. And on different levels, they try to, for example, create a case. So the case request is by the user is put on blockchain A, and then the mutual nodes, which can see both blockchains, kind of agree on that transaction and put it on the bridge chain. After that, the corresponding blockchain, which is blockchain B in this case, translates this and puts it, the mutual nodes between them translated and put it on blockchain B. So that's how blockchain A to blockchain B establishes a case. We also have our access control, which is implemented in each of the blockchains. And also because there's going to be a single investigation, in order for the investigation to move along, there has to be a voting, and all of the blockchains should be able to vote on the progression of the investigation stage. So one important concept was that sometimes we want to verify the information without sharing the information. And in that sense, what we do here is when there is an internal transaction and request going on about one case on, for example, blockchain A, the hash of it is sent to the bridge chain. And what bridge chain does is makes, again, a single Merkle root of that investigation on blockchain one, and it saves it. In that case, the other blockchains can simply ask the bridge chain for verification. And if the bridge chain verifies it, that means blockchain one has been honest about it. If it doesn't, that means a tamper or a breach has happened in the information. So you might ask, why do we even need a bridge chain? Why not just let the blockchain just connect to each other with the mutual nodes joining them? So this is possible, but as the number of blockchains increase, the bridge chain handles more communication requests than the simple method we saw in the last slides. So the average communication time per request stays about the same. But in other words, bridge chain scales to more blockchains, while the simple notary uses a fewer requests but achieves similar speed. Also, we have our provenance verification with bridge chain. We can do voting there. And we don't need any routing protocols going on when we have more than two blockchains trying to talk to each other. So also you can see here that how the number of the blockchains with mutual nodes increase when there are more than two blockchains involved, comparing it to bridge chain and all of the issues that I mentioned. Also, one important aspect that the other literature relating to cross chains hasn't really delved into is that usually when there is an intermediary between different blockchains, the bridge chain should scale when more blockchains join that network. And that is because we want to preserve the trust in bridge chain itself. And we don't want to violate the consensus of the bridge chain, which is a blockchain too. So what I mean is when the number of blockchains trying to communicate increase, we have to increase the number of trusted nodes of the bridge chain itself. So there are some open problems for the future work related to this specific concept that I talked about. One of them is adding AI and ML tools to see if the security is preserved. We need federated learning and digital forensics. And also we need automated tools for formal verification of blockchain and based provenance systems. Although universal composability is a good way, but it's prone to a lot of human errors, and it can also be complicated to do so. Also, the intermediary analysis for cross-chain is important, and it's not been very delved into in the past. It's good to see what would be the requirements for such intermediaries. So what we done today is we looked at blockchain-based provenance framework. We designed a blockchain-based blockchain framework for digital forensics for provenance named FrenzyBlock. We did a universal composability analysis on it, which is proving if it will be still secure in a modular concept if it is a part of other frameworks. We also looked at what happens if more than one agency is trying to connect to each other and different blockchains are trying to connect. So what this whole research is interest in digital forensics and also blockchain. So if you are interested in blockchain and you have another interest, for example, one of my students is interested in music and he was thinking about developing a blockchain which can be useful in music and capturing the provenance of different instruments. So you can look at the domain that you are interested in, and also if there are blockchains there, or if it's not, how can we add it? And it can be a very nice project for the future, or it could be a research idea. So thank you for listening.
Thank you very much, Asma, for a very interesting presentation. And thank you for leaving time for potential questions from students. And so I'm going to open up the floor now for anybody who has got questions. You can unmute yourself and ask, or you can write it down, but if you would go ahead and ask. And James has put the Qualtrics survey that you would put in before you leave. let me begin by seeing if there's anybody else got a question for Osmo. This is I think one of the first presentations we have had in CISR seminars around blockchain specifically, so it should be of interest to many. Anyone else got a question? While somebody thinks of question, I will ask you one. The universal composability is like a formal method to approach things. And in one of the places where you had shown proof, it looked like it's a proof that's coded, like it's an implementation. Can you comment on, and some students may think, including myself, when I hear the word proof, it would mean something that I would mathematically prove the correctness of something. So is there a different notion? What are formal methods' role in security, including this, that you can say something around what proof means and how it's achieved?
Sure, yes. So this is kind of it's not quite mathematical, but how it is that first we are defining the ideal version of the system, and you are just doing it. You're not implementing it. Well, the implementation is different. You're just saying what happens in different phases, and each time that we have like in an ideal world, we don't have leakage to the adversary. But in the real world, when different components of a system are trying to communicate together, maybe we have leakage to the adversary. So we will also define the real world, what is like the step-by-step happening, the entire flow of the system. And then we will have a simulator, which is kind of communicating with the ideal world. And we'll see if based on our design, even though there's leakage in the real world, is it kind of can be mitigated in a way which can be like the ideal world. So at the end, we will see if the real world emulates the ideal world. And this can be done in a few steps. And at the first, we have to know what we're exactly guaranteeing in our system. And if we get to a phase that we cannot really prove if these emulate each other, we have to lower our security guarantee. We'll say, okay, it doesn't guarantee this, or maybe we have to change something in our system, or we have to say it guarantees something else and try to prove that.
Okay, all right. So it's in that sense it is called a proof. So thank you for that explanation. Anyone has got a question or two?
I see in the chat, someone says, do you know what program the student is planning on building the music blockchain? No, I don't know yet. It's a theory right now that he would like to look into how he's going to do it.
Anybody else? We still have a few minutes, so there's time for asking questions.
Is any of you interested in a domain that you think a blockchain would be good to have there?
Well, that might be a difficult one to answer. It could mean that they have thought about this for a while, and
Yeah.
I'm sure this could plant some seed, and some people may start thinking about it. I would probably have been shy myself if I was to be asked it, unless you have thought about it before. So
Yes.
but I'm sure this would give some idea, and there will be a chance for students to be involved in research in the spring semester. And so we do have a number of things that are going on that project ideas would be collected, but this could be an additional one, I think, for some students at least.
I see in the chat like finance. They say finance is very interesting. Yeah, that's an important domain to use it. So
Are there any like general ways in which you could describe, for example, where blockchain is ideally suited? I know you've given some examples already at the beginning, but what is it that you could characterize as where this might be a way for students to think about what they might interest them? So how would you describe in a generic way where blockchain is a good solution? That's a question for me.
Uh, so, the way to describe it is if a few people are involved in, for example, if it's a collaboration or there are different operations going on, and they're not in the same place, so there needs to be like a distributed system in order to track it. We don't want the history to be changed. It's very important for us to verify the integrity, and we don't want anyone to be able to deny what they did on something. So that would be a great case for the blockchain to be there.
With that hint, anybody has then an idea for what they would use, or any other question? I'll give you a minute to do that. Otherwise, we will wrap up. Okay, then we've got a question.
So yes, and also no, but and blockchain can be studied in different aspects. You can study it in terms of cryptocurrency. For example, when I first started working with blockchain, I implemented the ASMA coin. So just wanted to see how blockchain works. So if you wanted things like that, Udemy would be a nice way of starting out with blockchains, like implementing your own version of Bitcoin or Ethereum and seeing how it works. But like if you wanted to design it as a framework for a domain that you're interested in, it's good to kind of read some of the scientific literatures or go into the documentations of the blockchains used, for example, in Walmart with IBM or etc., and see how they design it and go from there.
Good question. Well, looks like you did a good job explaining things. So that's one way to interpret it. So thank you very much. Yeah.
Yeah, I'm glad everyone learned that so much that they didn't have any questions.
Yeah. So
thank you, Asma.
You're welcome.
Yeah. Thank you very much for taking the time again. And students, remember to fill out the survey form. We will meet in